So here we are, we're back. Now we just sort of went over what a convolutional coder is and how this unit trellis comes out of it. All right, so now we're going to jump to like the receiver side of the problem. So the sender would have this coder. It would output whatever this coder outputs, right? And then the idea is that somewhere between the sender and receiver, there could be bit errors. Bits could get flipped. So we're going to express that. We have our received signal, R, is going to be equal to C, XORed with some errors, some kind of error indicator that's the same length as C. But the key is that the receiver doesn't know what errors were made. This receiver has no one has any way of knowing that. So what the Viterbi algorithm spits out is it's gonna give us the most likely sent sequence C, given the assumption that we made the fewest errors. Okay, which is a little bit. That's a little. Yeah, that's really what all it is, though, is that it's the most likely sequence. It could be some other sequence, but what the Viterbi algorithm is going to give us is the most likely one. So for our problem, we're going to just come up with an arbitrary received sequence R, right? Okay. So I'm going to say that R is equal to 0, 0, 0, 1. What did I say? Another 0, 1. Another 1, 0, and 0, 1. Okay. Sorry. Nope, I had this the other way around. I made some notes, and I gotta make sure the problem works out the same way. But this is arbitrary. And we could write down any random sequence of bits, and we should be able to decode it, find out what the most likely sent message was. All right, so this is all the receiver has to work with. Just this. They don't know what C was. There's no information about that. So what the receiver does is it runs this thing called the Viterbi algorithm. Now, one more assumption we are going to make here. Well, you might be wondering what all these dots I drew out are. This is the Viterbi algorithm is going to work step by step. Now, you see for our encoder, for each one input bit, we get 2 output bits. So we're going to work in chunks of 2 received bits at a time. So let's actually just rewrite this sequence. It helps to keep, it's not necessary, but it helps to keep track of what's going on by writing your received sequence up here broken up into length 2 chunks, basically. We got another 0, 1. We have a 1, 0, and another 1, 0. All right. So you could think of these, basically the dead space in between these columns as chunks of time, right? We have our 4 possible states at each time. And so we're going to kind of duplicate this trellis in each of these columns and see if we can figure out how our state machine evolved and therefore what the valid output is. Okay. One more assumption is that initially, when the machine starts sending, when we input our first bit, when our first bit is at the input node, the initial states are 0, 0. Okay. So remember how these columns of dots were kind of like our current state and the next state? So if we assume that our initial state of our machine is 0, 0, it means we start our process. We're forced to start our process in this state. Oh, these dots, these dots still correspond to these states over here, okay? This is a divider because this is a model of our encoder. And from here over is actually decoding a specific thing we got, okay? But really, these columns you'll see are just kind of repeats of this. So if we start in state 0, 0, that means it's impossible for us to be in any of these other states. So at first, all we have to think about are the 2 possible transitions, right? We could transition from, there's two paths out of this state. We could make this transition. And then what we're going to do, we're going to consider all possible transitions. And we have to, okay, so let me rewind just a bit. What I said earlier is we're going to assume the least amount of errors were made. Our this Viterbi algorithm is going to be working with just bit errors. Is the bit different or is it not? There's other ways to, there's other criterion to work with. The idea is that you just need to assign some kind of cost or value that you can minimize or maximize. So in this problem, we're minimizing the number of errors, okay? Yep, that would be called the Hamming distance of blocks. We'll see. Okay, so what we say is we consider this transition here. If we made that transition, we refer back to this, okay? If we made this transition, we output 0, 0, right? And we actually got 0, 0. This is what we received, our first 2 bits we received. So what we do is we compare what we would get with this transition to what we actually got. And in this case, we see we made 0. There's no difference. Our Hamming distance between the output when we make that transition and what we actually got is 0, right? 0, 0 has no difference to 0, 0. So this is somewhat arbitrary. You can keep track of this how you want, but we need to keep track of these costs or Hamming distances or weights or whatever we want to call them throughout the problem. So this transition results in a difference, a Hamming distance of 0. And I'll write circled little numbers. Actually, might not be. I might not end up circling them because it might take up too much space. All right, so we could have also made this transition. This will illustrate what I'm getting to a little better. If we make this transition, we have our input output. If we make that transition, we output 1, 1. Now that has a Hamming distance of 2 away from 0, 0. We would output 1, 1, but we receive 0, 0, so we have 2 errors, right? So we're gonna mark this with a little 2. Okay. Now for this column, we restricted ourselves to starting in this state, right? And that's usually what you'll run into with these. That's usually what you'll be given with these problems, is that you start in state 0, 0. There's no other transitions to consider for this first time step, right? We can't. There's only 2 ways out of that first state. All right. Now let's move to the next column. We could make this transition, or we could make this transition, right? Those are both valid. Now let's think about what the weights would be for those. Okay, so this is the key though. These costs have to accumulate across our problem, right? We have to add them up as we go. Because what we're doing is we're looking for the most likely total sequence, so we need those weights at the end to pick the most likely one at the very end and work our way backwards from there. So we'll keep track of them, add them up as we go. So we have this transition should result in an output of 0, 0. We receive 0, 1, so that's a Hamming distance of 1, right? And we have to accumulate it with the one from the previous time, which is, in this case, 0. So we have 0 plus 1 would be 1. All right, this transition should result in an output of 1, 1, and we received 0, 1. Now, again, that's a Hamming distance of 1, and when we accumulate that from the last, we get 0 plus 1 is 1. Okay, so now we have to consider a couple more. There's a couple more possible transitions because we could be down in this. We could be down in this state here now, right? This state can transition to either that state or this one down here. Now let's see if we can figure out our Hamming distances there. This transition should output 0, 1, and that's actually exactly what we got, right? We know our coder outputs 0, 1, and we received 0, 1. So the accumulated Hamming distance for that, well, for this time step, the Hamming distance is 0, right? But we have to accumulate it. It's 2 plus 0, 2. Now, finally, this transition should output 1, 0, and we received 0, 1. So there's a Hamming distance of 2 between our received and what we should get for that. So accumulated is 2 plus 2. We get 4 down here. Now, remember, we're trying to minimize, we're trying to pick the sequence that has the smallest value for this number. And it's tempting to just be like, let's only work from these two out, right? Because these have nice weights right now compared to these. The cost is much lower for those two. But we can't do that. We'll see in actually the very next step here how we can start eliminating paths, but we can't eliminate them based on just the weights sitting at those nodes. Okay, so the next step. All right, so since we restricted ourselves to starting here, we've kind of spread out slowly, and only in the second time step are we even possibly in all of the states. Does that make any sense, what I just said? At this point, we could be in any of these states, put it that way. So now, I personally prefer to, and there's two ways you could think about this. You could look at this state and be like, and consider the two transitions. What are the two ways to get out of this state? You could do that. Once there's a possibility of being in any state, I prefer to jump to the next column and say, what are the two ways into this state, okay? And the reason I prefer that will become evident pretty quickly. All right, so we want to consider the two ways to get into this state. That would be either across from here or up from down there, right? So let's consider both of them. And let's do their Hamming weight thing, Hamming distance thing. So this transition results in an output of 0, 0, which has a Hamming distance of 1 away from what we received. So okay, so this is kind of the issue right here. Look, we have two paths coming into the same node. Now, this is where we can start eliminating paths. So this path would have a Hamming distance of, an accumulated Hamming distance of 2, right? We have 1 here plus the 1 from there. And this path would have an accumulated Hamming distance of, that should output 1, 1. So we made Hamming distance of 1 plus 2. So this path has an accumulated Hamming distance of 3, right? We have two paths coming into the same node where one has a greater cost than the other. That is where we can eliminate one, and we eliminate the one with a greater cost, right? You know, when we're working our way backwards, if we came to this point and we had two ways to leave, and this one had a cost of 3 and this one had a cost of 2, you obviously want to take the one with the lower cost. So that's when we can just, I don't know what the best way to mark this really is going to be. Possibly just by putting an X. We'll just put a red X on paths that we dropped from consideration. Okay. All right. So, and we will not write the cost number for paths we drop from consideration as well. Just for, you can, but you might want to write them in a different color or something. Actually, you know what? That's a good idea. Let's do that. We'll write them in red. So the red costs are the ones that are higher, and the ones correspond to paths we're not considering. All right, what are the two ways into this node? We can come down from up here or come up from down there. Those would output, that should output 1, 1. That should output 0, 0. So either way, we have a Hamming distance of 1. And from here, that would accumulate up to 3. And from here, it would accumulate down to, or it would accumulate up to 2, right? Which is less. So we have 2 there. We have a Hamming weight of 3, or Hamming distance. I keep saying weight. That's not technically correct, I don't think. Hamming distance of 3 for that path. And again, we drop this path, right? Get rid of that. Not considering. So this process of dropping paths based on their costs when they're coming into a node, that's where we can do it. When they're coming into a node, we can decide between them. You'll see at the end that results in only one path backwards from each of these 4 points. That's what we get. All right, so let's keep going. For the two ways into this node would be from there or there, and from this way we would output 0, 1. From this way we'd output 1, 0. So this transition has a Hamming distance, current Hamming distance of 0. That's nice. So this this Hamming distance would accumulate to 1. And this Hamming distance would accumulate to, we'd have, the output should be 1, 0. We have 0, 1, and we have down here an already accumulated 4. So this would accumulate right up to 6, and we would compare 1 and 6, and we would drop that path. All right, one more node to consider. For this node, we can come down from up here, or we can come across from the bottom. If we come down from up top, we would get an output of 0, 1. Nope, 1, 0. And if we come across from the bottom, we get 0, 1. So that means that if we, right, so we have a Hamming distance of 2 for this transition, for this one, and a Hamming distance of 0 for this. This is a good point to make an example of why the accumulation part's important. So this transition on its own has a Hamming distance of 0 from what we received, and this one has a Hamming distance of 2. But we accumulate, and so we have 1 plus 2 is going to be 3, a weight of 3 down here, or a cost of 3, and we have 0 plus 4, right? So we get a weight of 4 down there, and even though this seems like a nice transition just in this snapshot in time, that goes away. All right, so we are going to keep doing the process, and I might try to say a little bit less for the next couple columns. Just try to follow along and see if what I'm doing makes sense. So consider the 2 ways into this. We have either from there or there. We're going to say this would be 0, 0. That would be 1, 1. Both of them would have a Hamming distance of 1. And so we get a Hamming distance, or accumulated Hamming distance of 2 for this path, and 3 for this path, top path, so we drop the top path. Okay. Next one, we can come in to this one from here or there. This would be 1, 1. This would be 0, 0. That gives us a Hamming distance of 1 for both current time. The accumulated would be, it would be 1 plus 1 for this path. It would be 2 right here. And it would be 2 plus 1 for this path. It would be 3 right here. So we drop this path from consideration. Now, let's see. From here, we can come down or up. That should output 0, 1 or 1, 0. So coming down, we have a Hamming distance of 2, so it accumulates to 4. Coming up, we have a Hamming distance of 0, so it accumulates to 3. So we have 3 here, and we have 4 here, and we drop the path that results in the higher one, drop 4. And then, let's see, we can come down from here or come across from there. That would output 1, 0, and that would output 0, 1. So we have a Hamming distance of 0 for that one and of 2 for that one. So this accumulates to 2, right? No. Let me double check what I just said. 1, 0. Yep, this would accumulate to 2 for this path. And for this path, it would accumulate up to 5, right? And we drop the 1, of course, that accumulates that much. And then our final step here. There's ways to end once we're at the last column. If you're doing an exam or something, you could end this relatively quickly. But I'll just do out the entire thing. All right, so coming into this one, we could come from over here or from down here. We would get a accumulated cost of it's 0. It's 1 for either one, so we get 3 or 2. We would get 3 up here, and we'd get 4 down here. So we drop this path here. For this one, again, the Hamming distance will be 1 for either transition, so it accumulates to 3 for this path, and again 4 for the bottom path. And so we drop that one. For this one, we can transition down or up. That's 0, 1. Coming up is 1, 0. So coming up has a Hamming distance of 0, or an accumulated Hamming distance of 2. Coming down has an accumulated Hamming distance of 4. We drop it. And then one final, okay. Yeah, no, let's just do the final one out. Yep. It can be that or that. This will have a Hamming distance of 2, and this one will have a Hamming distance of 0. And so we get we get a Hamming distance of 2 there, and a Hamming distance of 4 down here, right? 4, so we drop this. Now, we actually arrived at a kind of interesting scenario over here. If we look at our costs of our accepted paths all at the end, we actually have 2 different nodes that have, we have 2 different nodes that have a cost of 2, correct? So that means that it's really a coin flip as far as the most likely sequence goes. So you could really kind of coin flip which of these 2 we need to work backwards from. But let's say we decided to pick this one. Let's say we decide that one. And we can then work our way backwards to, is that right? Yep, that's right. Okay, so we picked our final node that has the lowest cost. If there's equal, just pick one of them. And if we trace backwards and we're careful to never go onto a path that's x'd out, we'll see there's only one path from here to the beginning. That's what's special about this algorithm. That's what it gives you. So we'll have, I'll kind of just circle them like that, I guess. It's a little bit messy looking, but so this would be the first. Then we can't go on that path; it's crossed out. So the next one will be this one. We're at this node. We can't go that way, so we go this way. And finally, we're pretty much restricted to go like that. Okay. So what does this mean? This means that we should be able to look at these transitions we've chosen and look at what C must have been, right? And we can actually figure out what the input was as well right away. So do I have space at the bottom there? Yeah. So this is telling us that C is equal to, we've selected our path by working backwards. Now, C would be what actually came out of the machine, right, without errors. And that's given by this description of the machine. So we're claiming at first we made this transition, so the first 2 digits of C must be 0, 0, right? Then we make this transition. Again, that's the same transition. Next 2 bits must have been 0, 0. We make this transition, which would be 1, 1. And we make that, which would be 1, 0. And we make this one, which would be 1, 0. Okay, so we could see that's slightly different than R, right? We have a bit different there and a bit different there, and that's it. So we switched 2 bits of our received sequence. That's the most likely sent sequence. This is going to tell us, usually probably on a problem, the teacher will ask for the decoded message, right? What was input to the machine. And that might sound difficult, but it's really not. All we have to do is go back, and we'll call it M message. All we have to go back is go back and refer to these same things, right? So we have this transition corresponds to an input. That's what we're looking for. What was the input? An input of 0. The next transition also corresponds to that same input of 0. This transition is an input of 1. This transition is an input of 1. And that transition is an input of 0. So let's make sure that makes sense. Our C should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 long. And remember, we erased it, but this is a rate 1/2 convolutional coder. That means our input was 1, 2, 3, 4, 5 long, right? So our output's twice as long as our input. That makes sense. And so yeah, so that's how the Viterbi algorithm works, and we use that to decode received anytime we know it was encoded that way. Hope that helps. Thanks for watching.